Now we are in a unit called Induction and Recursion. We've already talked a little bit about recursion in the last lesson, and so today we're going to switch over and start talking about induction. Then we'll learn about what mathematical induction is. We'll see a few proofs using mathematical induction, and then for the rest of the unit, which does involve several more lessons, we will be working each time within the context of either induction or recursion or sometimes both, okay? Because often they do go together quite well. So anyway, let's talk first about mathematical induction. Hopefully this is a little bit familiar to you. If you've had discrete 1 at this school, you've heard a little bit about mathematical induction. So hopefully it is a little familiar to you, but if not, I'm going to go ahead and try to explain it so that you will understand it even if you haven't seen it done before. Okay, so first of all, we're going to see a proof by mathematical induction. So here's the proof. Here's what we want to try to prove. We want to try to prove for every positive integer n, and we've got on the left side the summation as j goes from 1 up to n, and adding up all of the terms j, that is equal to n times n plus 1 over 2. So it's like a closed formula that we're being told is equal to that summation. So we can, that's a really good example where mathematical induction can be used quite simply in order to prove that. But what is mathematical induction? So there's two components of an inductive proof. First of all, the base case, and that's the case where we establish that the theorem is true for the first value in the sequence. Looking up here, you see that we're supposed to prove it for every positive integer n. So we at least prove it for the base case that it's true for the first possible positive integer n, and that would be 1, right? So we would want to prove this is true for when n is equal to 1. That would be the base case. So the base case establishes that the theorem is true for the first value in the sequence. Then we do the inductive step. That is going to establish that if we can assume that the theorem is true for n equals k, just any old number k, then somehow if we're able to we start with that assumption and then see if we can prove that that assumption then implies that the theorem also holds for any n k plus 1. So we prove it works for, we assume it works for some n, and we'll say this value where n is equal to k, and then we show that that assumption implies that it also is true for k plus 1. And here's the way our book states it. It says, let S of n be a statement parameterized by a positive integer n. Well, this is a statement up here, this theorem, this equation. It is a statement that's parameterized by a positive integer n. We have n here. Then it says, then S of n is true for all positive integers n if S of 1 is true. That would be the base case. So up here we would be looking to prove that if we put a 1 in place of n, that this is true. If we can show that that's true for n equals 1, then we will have proven the base case. And then 2, for all k in the positive integers, S of k implies S of k plus 1. Again, meaning if we assume it's true for n equals k, then we try to see if we can prove that it's also true for S of k plus 1. And if we can prove that, along with that base case, then those two together go together to being to making the case for that statement to be true. Now, inside the inductive step, we're always going to make an assumption and then try to prove something else. We're going to assume that the statement is true for n equals k, and then we're going to try to prove that based on that assumption, we can show that S is true for k plus 1. So the thing that we assume within the inductive step is called the inductive hypothesis. So the inductive hypothesis is always the assumption. We're always assuming that the statement is true for n equals k, for any k in the positive integers. That's our assumption, and then we need to prove that it's true for k plus 1. But anyway, sometimes people get the inductive step and the inductive hypothesis mixed up. So the inductive step involves making an assumption and then proving something else. But the assumption itself is what's called the inductive hypothesis. So I'll try to point that out as we go through our proofs. I'll try to point out when we're on the inductive step, and then also what the actual inductive hypothesis is. Okay, so let's see if we can prove this theorem. This is the theorem that we just saw in the previous slide. Does this theorem hold true for when n is equal to 1? Okay, so that would be j equals 1 up to 1. Does that equal? That's the question. Does that equal? And let's figure out what that would be over here. It would be a 1 times a 1 plus 1 over 2, right? So if we can show that this over here on the left is equal to this, then we've proven the base case. Well, let's see, what is j equals 1 up to 1? It's just equal to 1, right? We just have the one term, 1. And that's all. Well, does 1 equal what we have over here? That's where we're going with this. We want to try to prove that these are equal. Well, if we take a look, we see that inside the parentheses, that's just a 2. And then we're dividing by a 2. So remember that we can always take any number, multiply by something, and divide by the same thing, and we aren't changing the value of the number. So I can take 1, multiply it by a 2, and then multiply it by a 2, and then divide by a 2. I'm not changing the value, right? Because, I could just cancel these 2's out. But I'm not going to do that. I want to write it like that, because then I can say, well, that's equal to 1 times 1 plus 1, because 1 plus 1 is a 2 over 2. So that's what we were trying to prove, right? We were trying to prove that it's equal to that, and we did here. So basically we just put a 1 in for n, and then just double check to see if we could write what the answer is in the form that looks just like this. Okay, so that's what we would have. Okay, so it's true. This is true for n is equal to 1. So now we go on to the inductive step. So with the inductive step, we're always going to assume that the statement is true for n equals k, and then try to show that it's also true for n equals k plus 1. And remember, so assumption always starts first within the inductive step. And the assumption itself is called the inductive hypothesis. So what would be the inductive hypothesis? Well, we are assuming that it's true that this theorem up here is true for n is equal to k. So I'm going to say j equals 1 up to k of, and it's the summation of the j's, equals k. I'm just putting k in place of n. Okay, that's what we are assuming. This is our inductive hypothesis. Now, remember, we haven't proven this yet. but we're saying we're going to assume it's true for k and see if we can prove that then it would also be true for k plus 1. And if we can do that along with the base case, then we've shown that it would be true for all n. So we're going to assume this, and then we're going to try to prove what? Well, we want to prove that it's true for k plus 1. So j is equal to 1 up to k plus 1 of j is equal to, well, we're going to put k plus 1 in the place of this n up here. So it's going to be k plus 1 times that plus 1, so it's k plus 2, right? K plus 1 plus another 1 is a k plus a 2 over 2. That's what we want to prove, okay? So this is what we're looking for here. We're hoping to get to this. Now, if we want to prove this, then I always say, you know, we write the assumption over here on the left, and then to prove this, it's the thing on the right that we're trying to prove. So I want to take what's on the left of this statement on the right, this here, j equals 1 up to k plus 1 of j equals, okay, I start with that. Then I use what I know here. I'll change colors here. I'll use this at some point and then hope to eventually get to find that it equals this. And if I can do that, then I have performed the inductive step. Okay, so let's go back to where we were at. We're starting with this. We're looking at the summation as j goes from 1 up to k plus 1. And what do we know? All we know is we can assume this, the inductive hypothesis, but that's all we can assume. Well, there's one other thing that we can do first. And remember, we learned that little trick that you can pull out a term from a summation if it's going to help you in some way. I'm going to pull out the final term of that summation on the left here. So I'm going to go j equals 1 up to only k, not all the way up to k plus 1. Okay, so I'm stopping one term early. But remember, if we do that and we want to say it's equal, we have to then explicitly state that last term that got left off. So what would that last little term be that got left off? That would be when j is equal to k plus 1, right? So it would be k plus 1 here. That's our last term. We pulled out a term. Okay, so we have that. Now, why did we do that? Because we want to use our assumption. Remember, we're trying to find a way to use this assumption that we have here, that we're assuming for our inductive hypothesis. Now I can use that, right? Because I have this thing, whoops, sorry, I wanted to change the color. It's not changing, sorry. This right here. We know that is equal to this up here because that was what we just are assuming. So I'll say that is equal to k times k plus 1 over 2. Okay, so we're just assuming this is equal based on this assumption right here. Then I have to go on and add this k plus 1. Now, remember what we're trying to get to. We're trying to get to this over here. So it doesn't quite look like that yet. So, you know, we might want to just play around with the arithmetic kind of and maybe see what we could get. I might think this, you know, there's probably several ways to go about it, but I'd say, well, if I want to get to where what it is up here, notice it's all together in one fraction with a 2 down there. So maybe let's go ahead and get a common denominator here between this k plus 1 and what was already there in the first term. So I'm going to divide by 2 and then multiply by 2, right? We can always do that. Take something, multiply by 2, divide by 2, we end up with the same thing there. So I'm going to do that. Okay, so now what? Okay, there's a couple ways you could go here. You could simplify everything, put it all together, and then factor it out. But there's even another way here that's a little more straightforward here. Let's put it together in one fraction. So it's all over 2. And I've got the k times k plus 1 plus, and let me just write this as a 2 times k plus 1. So all I've done is put it together in one expression. One expression there at the top. Now, here's where some people might go ahead and multiply this out and then eventually have to factor. But look at this. We've got a common factor. K plus 1 is there and k plus 1 is here, right? So that means that on the top, I can factor out a k plus 1, right? K plus 1, factor it out. What do we have? Well, for this first term, once we factor out a k plus 1, I'm left with a k. For the second term, once I factor out the k plus 1, I'm left with a 2. So I have k plus 2. And that is all over 2. And guess what? That is exactly what we were trying to prove there. So we proved that the summation going up to k plus 1 is equal to k plus 1 times k plus 2 over 2. And that was exactly what we were trying to prove right here. So again, what I like to do when I come to the inductive step is first write out what I'm assuming, then write out what I need to prove, and then start with, let me see if I can get a good color here. Start with, I'm going to change it to a color we haven't used yet, green. Okay, then I always start with the left-hand side of what I'm wanting to prove. See how I started with that? And then somehow I try to end up with the right-hand side, which is what I did here. Okay, sorry for all the writing, but hopefully you I just want to make sure you see what I'm doing and understand what happens here. Now, sometimes we're trying to prove something, that something is true for all n greater than or equal to some other number besides 1. So maybe we're not saying it's true for every value greater than or equal to 1. Maybe some statement is true for every value greater than or equal to 3. So, what they're saying here at this point in the book is that if our statement is only, we're only trying to prove it holds for some constant c other than 1, then our base case changes, right? Then we're not going to have to prove the base case for s of 1. If we're trying to prove it's true for all values greater than or equal to 3, then the base case we would need to show that the statement is true for 3, right? So it's just saying that if it's not 1, maybe the starting point is a number greater than 1 there. So the base case would be showing that it's true for s of c, if that's really what we're trying to prove. Then the inductive step is going to establish that if we can assume that it's true for k, then it's true for k plus 1, as long as k is greater than or equal to this c. Okay, so we always have to, double check. We're going to be using this as part of the, something we always know that we're assuming it's true for k, as long as k is greater than or equal to c. So then we have to prove it's true for k plus 1. Same thing. So an inductive proof assumes that S of k is true where k greater than or equal to c, and then uses that fact to establish that S of k plus 1 is true. So really the only difference here, and I hope I'm not confusing you, is that we've had this extra little thing here that we add on there, whereas before it was as long as k greater than or equal to 1. Now maybe we would only care about all k's greater than or equal to some other number like a 3. Okay, so let's look at this example here. This theorem here is saying it's true for n greater than or equal to 4. So in this case then, we don't have to show that it's true for n equals 1 or 2 or 3. We just have to show for the base case that it's true for n equals 4, because that's where we're starting here, right? And true for n greater than or equal to 4. So we'll check, is it true for n equals 4? Okay, well, we would put 4 in for n, right? So I've got 2 to the 4th. We're trying to find out, is that equal, greater than, or equal to 3 times 4? Okay, right? That's what we would have if we put a 4 in for n. So that's what we're trying to prove. We don't know that yet. Well, let's start with 2 to the 4th and see what's that equal to. Well, that's 2 times 2 times 2 times 2. So that's a 16. Now remember, this is a 12 right here. This is 12. So what I could do is look at that, write this 12 down here, and say, what do I know about 16 and 12? Well, 16 is, in fact, greater than or equal to 12. Now, you say, why do I put or equal to? Because 16 is not equal to 12. It's just greater than 12. But remember, what we're trying to prove is that it's greater than or equal to. So that's all we have to prove. So we'll go ahead and say, yes, I know for a fact that 16 is greater than or equal to 12. In fact, it's greater than, but we'll go ahead and leave it as greater than or equal to, because that's what we need to prove for the base case. But 12 then is 3 times 4. So we've shown that for n equals 4, 2 to the n is greater than or equal to 3 times n. Okay, so that is the base case. Now we'll move on to the inductive step. So for the inductive step, remember that we're always starting with an assumption, and then we have to try to prove something. So what's our assumption? We're going to assume that it's true for all numbers n equal k, where k is greater than or equal to 4, and then try to show that it's also true for n is equal to k plus 1. So our assumption here, which we call then the inductive hypothesis, is going to be that it's true for k. So 2 to the k is greater than or equal to 3 times k for k greater than or equal to 4. Okay, that's my assumption. Now what am I trying to prove? I'm trying to prove that 2 to the k plus 1 is greater than or equal to 3 times k plus 1, right? Because we're just replacing the n with the k plus 1. Okay, so remember, over here on the left, this is what we're assuming. On the right, this is what we're trying to prove. Since this is what we're trying to prove over here on the right, I'm going to start with the left-hand side of that. So I've got 2 to the k plus 1. Okay. Now, remember, we need to try to get to the point where we can use this assumption. This assumption involves 2 to the k. So we might think, oh, well then let's see if I can write this in terms of, 2 to the k. So remember, 2 to the k plus 1, that just means we're taking 2 times itself k plus 1 times, right? But that would be equal to 2 to the k times one more 2, right? Because 2 to the k plus 1 would be the same thing as 2 to the k times 2 to the 1. So we can write it that way. If we write it that way, then I can make this assumption and say, let me get rid of that equal sign here. I'm going to say greater than or equal to, and what I'm doing is I'm coming over here and replacing that 2k with 3 times k. 3k, that's based on that assumption, and then times another 2, right? So let me see if I can do something like this. The 2k is greater than or equal to the 3k. So see that? I'm just kind of doing that to show what's in the red is what we knew to be true. So if 2 to the k times, then 2 to the k times 2 is greater than or equal to 3k times 2, right? Again, we're assuming that that's true for any k greater than or equal to 4. Now, what are we trying to prove? Remember, we're trying to get to this point right here. So let's see, we've got a 3 times k, 3k times a 2, but we want to somehow get to 3 times a k plus 1. So sometimes these would take a little bit of, might have to think about it a little bit, and you're really not going to have to come up with a lot. Well, you definitely need to follow along in these proofs and know what's the inductive hypothesis and all of that. But some of these take a little bit of creativity, and you might have to, if you were left to do this by yourself without any help, deciding how to come up with showing that this is true, it might take longer than what I would expect. I would not expect you to come, use some creativity on a test and come up with some great proof like this, okay? So I guess what I'm trying to say is you might say, well, I might not have thought of that, and I understand that, and don't worry, you're not going to have to think about some creative way to prove something on a test. You do, though, as I said, need to really understand what is the inductive hypothesis and then be able to follow along on the proof. Okay, so anyway, 3k times 2, well, we could at least do this. That means there's 2 of the 3k's, right? So 3k plus another 3k, right? Because it was 3k times 2. But now, remember, we're trying to get up to over here 3 times k plus 1. So I'm going to do this. Do you agree that 3k plus 3k is greater than or equal to 3k plus 3? Well, let's see. K, remember, is greater than or equal to 4. And, as long as it's greater than or equal to 1, then this inequality would be true, right? Because if k is 1 here, then this is an equality. 3k plus 3 equals 3k plus 3, right? But if it's, but we don't really care for it to be 1. We're in fact saying it's greater than or equal to 4. So if it's 4 or greater, then for sure what's on the left here is greater than or equal to what's on the right. So by dropping that k, that's just what we did, is we dropped the k, and we know since k is greater than or equal to 4 that by dropping the k, we're only going to be getting smaller. So this greater than or equal then would hold. But then, why did I do that? Because this, I can factor out the 3. So by factoring out the 3, I get this, which is what I was supposed to prove. So remember, if we've got a long string of equalities along with inequalities, as long as the inequalities stay the same, like I have a greater than or equal to and a greater than or equal to there, and everything else is equal to equal, then I can say that what I started with over here is greater than or equal to what I have over here. So let me just restate that then. So that means that 2 to the k plus 1 is equal to 3 times k plus 1. And that's true. We know it's true for k greater than or equal to 1, but we didn't even need to go that far because they were only asking us to prove it for bigger than, greater than, or equal to 4. So anyway, but this is what we've done. We have gone ahead, we've made our assumption, and then we've proven, starting with 2 to the k plus 1, proven that that's greater than or equal to this 3 times k plus 1. So this long thing here then shows that I've proven this. Shows that it's true for k plus 1. So I've shown the base case is true. I've shown that if it's true for k, it's also true for k plus 1. And so therefore it's true by induction. The next section is just called more inductive proofs. So it just goes over quite a few other proofs that are used that use mathematical induction. So we'll just go over some here today, and the idea is that if you see more and more of these done, that you'll become very familiar with the different parts of an inductive proof, and you'll be able to state what the different parts would be, and then would be familiar enough to be able to maybe even come up with a proof yourself. Although you won't be necessarily coming up with entire proofs on the test. Now there might be some ones in the within the practice problems or the assignments where you have to come up with the entire proof. I won't make you do an entire proof on the test, but I will ask you to identify the different parts of an inductive proof. So that's kind of the goal here, is for you to be very familiar with the different parts to the proof. Okay, so we're going to look at this theorem that says for every positive integer n, 3 evenly divides 2 to the 2n minus 1. So we're going to prove that by mathematical induction. Well, first of all, remember what this word divides means. That means that if we're going to say 3 divides this, then that means, I'm going to go ahead and say this means I'm going to go ahead and do that. This means that we can write 2 to the 2n minus 1 as a multiple of whatever it divides. So it would be times 3. So I'm going to say 3 times, I'll just put some integer in here. So if we can prove, that's what we're trying to prove, that we could always write 2 to the 2n minus 1 as 3 times some integer. That would mean that 3 evenly divides this, right? Okay, so this is supposed to be true for every positive integer n. So that means the lowest number we need to show it for is n equals 1, because n is the smallest positive integer. So let's see if we can prove it for n equals 1. Well, what would that mean? That would mean we're asking, is it true for n equals 1? That's the same thing as saying, does 3 evenly divide 2 to the 2 times 1 minus 1, right? Because we're putting a 1 in for n. Well, let's see. 2 to the 2 times 1 minus 1 is equal to 2 squared minus 1, which is equal to 4 minus 1, which is equal to 3. So does 2 to the 2 times 1 minus 1 divide, does 3 divide that? Yes, because it's equal to 3. 3 divides 3. I'll say 3 does divide 3. So it's true for n equals 1. Okay, so again, we just showed that this expression here is equal to 3. So does 3 divide that? Yeah, 3 divides 3. We know that. So it's true for n equals 1. Okay, so now the inductive step. We need to assume it's true for n equals k and then try to show it's also true for n equals k plus 1. So the assumption, remember, is what's called the inductive hypothesis. It's what we're assuming. Okay, so what are we assuming? We're going to assume that this is true for n equals k. So we'll assume that 3 evenly divides 2 to the 2k minus 1. Well, in other words, this means two to the 2k minus 1 equals 3m, where m is an integer, right? Okay, now if that's true and we're making that assumption, I'm going to go one step further and I'm going to add 1 to both sides. So then I could say 2 to the 2k is equal to 3m plus 1. Now the reason I did that, and you might not know that you would need to do that yet, but remember we need to use this assumption while we're trying to prove that it's also true for n equals k plus 1. And it's going to end up that if we write it this way, we can replace the 2 to the 2k by this. Okay, so just take that for what it is. Later I'll show you how, if you hadn't gone that far yet, you might have then seen, once you get to this certain point here in a minute, you'd see that you'd need to go this one step further and write it this way. Okay, so that's our assumption. We're going to assume that that's true. So now what do we need to prove? We need to prove that 3 evenly divides 2 to the 2 times k plus 1 minus 1. Okay, so how are we going to prove that? Well, first of all, let's remind ourselves what that means. And remember, this means 2 to the 2 times k plus 1 minus 1 is equal to 3 times some integer here. I'm not going to call it anything in particular. We just need to show that it's times some integer, whatever it would end up being. Okay, so let's start then with this left-hand side here, over here, and see where we can get here. So 2 to the 2 times k plus 1 minus 1 is equal to, let's distribute that 2, so we have 2 to the 2k plus 2 minus 1. And we could write that 2 to the 2k plus 2 as 2 to the 2k times a 2 to the 2, right? And then all of that minus 1. But now here's where we can replace this 2 to the 2k with what we know it to be over here. So if you hadn't gone this far yet and we're still up there, then you'd say, oh well, I'll just go a little further, one step further, so that I can know what 2 to the 2k is, so I can replace it. So so then 2 to the 2k then we know is equal to 3m plus 1, and we have all of that times 4 minus 1. And now let's distribute that 4 in we're going to have the, I'm going to continue to write it as 4 times 3m plus 4 minus 1. And then I'll write that as 4 times 3m plus 3, right? 4 minus 1 is a 3. And now I'm going to factor out the 3. 3. And what's left? 4m plus 1. Okay? Now, if m is an integer, and that's what we said over here, we said that m is an integer. Then, if m is an integer, 4m plus 1 is an integer. So we've proven what we needed to prove, that this expression 2 to the 2 times k plus 1 minus 1 can be written as a multiple of 3, 3 times 4m plus 1. So that is our proof. We've proven it for the base case, then we assumed it's true for n equals k, and then showed that it was also true, if we're making that assumption, that it's also true for n equals k plus 1. Sorry, I'm about ready to sneeze. In this section, they also talk about using induction to prove an assertion about a recurrence relation. So we're going to start out with a recurrence relation here. We have a sequence C sub n that is defined this way. C naught is equal to 5, and then C sub n is equal to the previous term squared for all n greater than or equal to 1. And we're supposed to prove that for n greater than or equal to 1, C sub n is equal to 5 to the 2 to the n. So that's just not 2, we're not taking 5 to the 2n power, we're taking 5 to the 2 to the n power. So it's kind of like a nested exponential there. Okay, so that's what we are wanting to prove. So first of all, for the base case would be for n equals 1, because we're supposed to prove it for n greater than or equal to 1. So let's see if it's true for n equals 1. That would be C sub 1 equals, well, what is that based on its the definition of the sequence? It would be C naught squared. And C naught is 5, so it would be 5 squared. And does that equal 5 to the 2 to the 1? Remember, we're trying to show that it's true for n equals 1. And yeah, you know, 5 squared is the same thing as 5 to the second power to the first power. So this is true. I could just rewrite it this way, and therefore I've shown that this very thing is true for n is equal to 1. So that's true for the base case. So now let's go on to the inductive step. And remember, for the inductive step, we make an assumption. So the assumption is going to be that it's true for n equals k. So that means we're going to assume that C sub n is equal to 5 to the 2 to, I'm sorry, not n. Let me start again here. C sub k is equal to 5 to the 2 to the k. Okay, we're assuming that. And then we need to prove that C to the k plus 1 is equal to 5 to the 2 to the k plus 1. Okay, so let's again start with this left-hand side of that statement we're trying to prove. c to the k plus 1. Well, what do I know that to be based on the definition? Well, it's the previous term, so that would be c to the c sub k squared, right? So it'd be c sub k, and we're squaring that. That's the definition of the sequence. Okay, but now we're going to use this assumption here, and so I'll replace those parentheses inside the parentheses with 5 to the 2 to the k. But then I have that for c to the k, but then I'm squaring it because I have this 2 here. So I'm taking 5 to the 2 to the k, I'm squaring it. Now how could I rewrite that? Well, that's the same thing as, let's see how to explain this. It's when we have an exponent on the outside of parentheses and an exponent on the inside of parentheses, remember that we would multiply exponents together. So this is 5 to the 2 to the k times 2. Okay, hopefully you see that. I've got this exponent on the inside of parentheses, this on the out. I multiply those together. And so that's 5 to the 2 to the k times 2, but I can write that. I'm trying to get it to look something like this. And I can write it as 5 to the 2, and that's in k plus 1. If there's an extra 2, then if we have 2 to the k and then times another 2, that's the same thing as 2 to the k plus 1. So I've proven that. I started with c sub k plus 1, and then I've shown that it's equal to what I wanted to prove. So if it's true for k, it's also true for k plus 1. And since I also proved the base case, then I can say that by induction, this is also true. This is true for all n greater than or equal to 1. I wanted to go over one more example. They proved this in the book in this section. This was a theorem that we talked about earlier. It was the closed form for the sum of terms in an arithmetic sequence. So we have an arithmetic sequence. It's a summation going from j equals 0 up to n minus 1, and we have the initial term plus j times that common difference. Anyway, that is equal to this formula on the right. And so we had used that the other day, and this is something that is nice and easy, fairly easy to prove using mathematical induction. So I'm going to go over it. I'm going to write out some of it, but some of it I'm just going to use what the book has printed out. But we're going to kind of go over the whole thing, so hopefully you understand everything. So the first of all, they showed that if we want to prove this, we need to prove it for the base case. So I'm going to just kind of write what that was. I don't have it here, so let's go up here and say this is how we prove it for the base case. If we were to prove this is true for the base case, we want to prove it for n is equal to 1, right? So I'm going to start over here on the left here and replace n with 1. So we have j equals 0 all the way up to n minus 1, which is 1 minus 1, right? 1 minus 1, which of course is 0 there. So, and then we have a plus jd, and that is equal to, we just have one term in here, and that's when j is equal to 0, because we're going from 0 to 0. So we have a plus 0 times d, and that's equal to just an a. And how are we going to write that? We want to try to write that in this term, so in this format. So what are we going for here? Let's kind of cheat just a minute to see where we're supposed to end up over here. Okay, so I'm gonna what would this be when n is equal to 1? It's going to be a times 1 plus d times n minus 1, so that would be 0, times and then n, which is a 1, over 2. So that's where we need to get. Okay, so let's just try to get there. So a is the same thing as a times 1 plus 0. You might think, why am I doing that? Well, remember, we want to write it like what's over there on the right, so I'll say a times 1 plus, and then I want d times 1 minus 1, or 0, times 1 over 2. So I just went up there and I realized that's equal to 0. So I can replace this. I can replace the 0 with all of this. So I'm able to do that, and so therefore I have what I need. I've proven that it's true for n is equal to 1. Okay, so again, I ended up just with this equals a, but then I went over here and said, well, no, I need to say that it's equal to this. And then I saw, well, this whole thing here is just equal to 0. And this is a times 1, so I'll just doctor this so I can write it that way. So I wrote the a as a times 1, and then I know I can always add 0, and then I replace the 0 with this here, and then I had what I wanted. Okay, so that showed that it's true for the base case. Now let's talk about some of this other stuff. We've got, they said, here's the inductive step. Here's the inductive hypothesis that it's true for k, for n equals k, right? So we're replacing the n everywhere here in the original with k. So we're assuming it's true for k, and then we need to prove it's true for k plus 1. So if I put k plus 1, and let's go back to this original, if I put k plus 1 in for n, see that k plus 1 goes in the place of n, then I'm going to have k plus 1 minus 1, which ends up being a k. So by putting k plus 1 in for n, it actually ends up looking like this, j equals 0 up to k. Okay, so we have that times what we have here in the summation, and we need to prove that that's equal to this formula here after we plug in k plus 1 for n. Okay, so let's see what they did. So again, just like I usually do, they started with the left-hand side of what we want to prove. And then what did they do here? Can you tell what they did? They pulled out a final term. They wrote the summation, stopped one short, and then this was the final term here. So then they had the final term explicitly down there. Okay, then let's see. Now here I'm going to use, let's see what color. I'm going to use purple. Let's see if that works. This whole thing here, we know by our assumption, is equal to dk times k plus 1, right? So we replace that. So, oh no, I forgot the ka here. So it's all of this here. So we're going to replace that summation with all of this. Then they needed to do a few things. They switched the KD and the KA around, got a common denominator with the KD, so that then they could put all this together. They factored out a D, and then ended up with this trinomial here. Well, no, not a trinomial. it's just 2k plus k squared minus k, so that's the same thing as, well, let's go ahead and write that. That's going to be, let's see, I'm going to just do this so that we write the whole thing out. Is a times k plus 1 plus, and then d, and then inside here it's just going to be a k squared plus k, right? All over 2. Okay, d k squared plus k all over 2. And so then they factored out a k from here and ended up with this. Okay, so a k came out of the parentheses, and so now we have a k out here with the d. And then we take a look and see, is that what we were trying to prove? That's what we're trying to prove here. So this is one that would take some creativity, and I would not expect you to be able to know, I mean, if you had enough time, you could probably come up with this, but you'd have to know, let's bring that KD over here, let's put the KA with the other, and blah, blah, blah. So anyway, what I'm trying to say is that this is the kind of thing that you aren't going to have to be doing for a test, something to this extent where you have to juggle a lot of different terms around and try to get it into this form that you need it in. There's some simpler ones that I think you'll find in the assignments that you might be expected to be able to do, but something that takes some creativity like this, I'm not going to make you do it for an assignment or make you do it on the test. Just remember, what you would need to do is to be able to come up with what you need to show. Well, it's always pretty easy to prove the base case. So I might ask you to prove a base case. But then aside from that, you need to understand what is the inductive step, what is the inductive hypothesis, and then be able to follow along to see that yes, indeed, if we've proven, if we've made this certain assumption and we've proven it's true, then also for n equals k plus 1, then we can say by induction it's been proven. So anyway, this then we would say is the proof for this closed form for the sum of terms in an arithmetic sequence. Okay, so those are all of the proofs that I wanted to go over for you. In addition to the problems that you have in your assignment for these sections, I would suggest, if you want a little extra practice, to work some of these additional assignments. So these are these extra exercises that are there at the end of of each section, and these are ones that I've opened up the solutions for. So you should be able to go in there and see the problem, and then if you have trouble, then you can view the solution, and all of these are just part B for each of these exercises. So take a look at those too if you'd like some extra practice.